Last time we started with the definition of pi and used some geometry to estimate its value. The ancient Greek mathematician Archimedes blazed this trail for us thousands of years ago. Thanks, Archimedes. Pi is defined as a circle's circumference divided by its diameter. This is seen in the image here as the purple circumference over the blue diameter. Last time we used two hexagons, the red one inside the circle and the green one outside. Geometry helped us find the inner perimeter and the outer perimeter. This gave us a lower bound and an upper bound to estimate pi. Those values are summarized here. If you care to see the details, check out the previous lesson. Notice that 3.23 is not quite 3.14. The question was posed last time, how could we improve our estimate? Well, a hexagon only has 6 sides. What if we increase the number of sides on our polygons? Here I have doubled the number of sides from 6 to 12. The inner perimeter is still smaller than the circumference, and the outer perimeter is still greater. However, both the red and green polygons hug the circle a little more closely than the hexagons did last time. This should lead us to suspect we can get an estimate for pi closer than last time. Let's find out. We still use sine for the inner polygon. However, we now use 15 degrees instead of 30. We doubled the number of sides, 6 to 12, so we divide the angle measure in half. The value for h is shown in red. You can plug those numbers into your calculator to verify them. In a few slides, I'll cover how we can calculate the sine of 15 degrees. This time we have 12 sides, so we multiply h by 24. This gives us approximately 6.21. Divide that by the diameter, 2, and we get a lower bound of 3.1058. Pi is greater than that value. Good. Now the outer polygon. The green height h is tangent of 15 degrees. Remember, this is the unit circle. Radius is 1. That keeps things simple. Again, we multiply h by 24. That gives us 6.43 approximately. Divide that by 2, the diameter, to get an upper bound for pi. Pi is in fact less than 3.215. Good. Now how do we calculate those values for sine of 15 degrees and tangent of 15 degrees? We can use the half-angle identities from trigonometry, which are summarized here. These were derived in a previous lesson, if you care for more details on their origin. Sine of 15 degrees is calculated here. We know the value of cosine 30 degrees, root 3 over 2. This comes directly from the equilateral triangle. Plug those values in and we get the number boxed in orange. Verify this for yourself on a handheld calculator. Choose between the built-in functions and doing it the long way. If you choose the long way, you can use Newton's method to calculate square roots. This was also covered in a previous lesson. In a similar manner, cosine of 15 degrees is calculated here. While not needed directly in our present situation, we do need it to find tangent. Tangent is defined as sine over cosine, so that is calculated here using the values from the past 2 slides. These are indeed the same numbers shown earlier in this lesson. If your calculator has built-in trig functions, pushing 15 tan should get you the number boxed in orange. Just make sure your mode is in degrees, not radians. Back to our lower and upper bounds. When averaged, these give us approximately 3.16. While still not equal to pi, we are a lot closer than we were last time using hexagons. Even the range between the lower and upper bound is smaller than it was with hexagons. It seems like we could keep squeezing these to get even closer to pi. How do we do that? I'd suggest we keep doubling the number of sides on our polygons. Before we get there, let me just summarize our results from the hexagon, n equals 6 sides, and the dodecagon, n equals 12 sides. These numbers come from what we just saw in the last slide and the previous lesson. There are only 2 rows thus far. Notice that 15 is half of 30, and 12 is 2 times 6. The last 3 columns are for inside perimeter, outside perimeter, and their average divided by 2. These should look very familiar. Now just a quick recap of how we calculate the value in each column. The angle theta, in degrees, is half the value directly above it. 15 is half of 30 in this case. The number of sides n is 180 divided by theta. Inside perimeter is 2 times n times sine theta. Outside perimeter is 2 times n times tangent theta. Our estimate of pi is inside perimeter plus outside perimeter divided by 4. That was just a demonstration on the second row, but the same rules apply for every other row in the table. Following those rules will give us these numbers. For each new row, we cut the angle theta in half. Remember that we can use the half-angle identities to evaluate sine and tangent, if you choose not to use built-in functions on your calculator. Look at the third and fourth columns. As we go down, those values for inside perimeter and outside perimeter get closer and closer to each other. We know the value of 2 pi must be squeezed between them. Thus we are converging on an answer. I would encourage you to make your own spreadsheet and verify these values for yourself. Make sure we are getting the same answers. The process of actively doing so will greatly enhance your understanding. Passive observation of someone else doing the math will only get you so far. Trace your eyes down the last column and notice that we gain a digit of accuracy every couple iterations, more or less. By the 12th row, we have about 7 digits past the decimal. This entails a polygon with more than 12,000 sides. At this point I have stopped drawing polygons. 12,000 sides would be hard to visually distinguish from the actual circle. Thankfully, we have developed a mathematical method that allows us to keep extending as far as we desire, even if we don't have a picture to look at. Here I repeated our estimate for pi in the second column. In the third column, the error for each row is calculated as our estimate of pi minus the exact value. The fourth column is the negative base 10 logarithm of the error. As discussed elsewhere, this gives us a quick way to evaluate the number of digits of accuracy. Of course, it only works if we know the exact value, for comparison's sake. That's not always the case, but lucky for us, pi is quite well known to a very large number of digits past the decimal. Here is a plot of that data. It looks like we get about 0.65 digits of accuracy with each iteration. This linear trend looks very similar to our results for Machen-like formulas. However, remember that Archimedes' method involves trigonometry, and those trig identities require taking square roots. This increases the computational complexity of the overall approach. That's just some food for thought. At any rate, this turned out to be a decent approach to finding digits of pi. Historically speaking, Archimedes didn't have the luxury of modern mathematics with decimal notation and trig identities, much less an electronic computer. All calculations were done by hand. As such, he had to stop after only a few iterations. Nevertheless, his genius shines through. He may not have found 100 digits of pi, but his way of thinking was spot on. In fact, Europeans wouldn't fully embrace concepts of convergence for a long time after Archimedes was gone. He was truly ahead of his time. That concludes another lesson. As I mentioned before, please make your own spreadsheet and play around with these numbers. I stopped at 12 iterations and got 7 digits of accuracy past the decimal. How many can you get? Feel free to utilize the comment section below for a discussion on this topic. If you enjoyed the video, please like it and consider sharing it with a friend. If you want to be notified when future lessons come out, subscribe to my channel. I appreciate your support and look forward to seeing you again.